Here's a really fascinating result of Einstein's theory of special relativity, which he published in a paper called On the Electrodynamics of Moving Bodies in 1905. And it's special in the case that it only deals with motion that's to do with constant speed or for stationary objects. That's why it's special relativity. And it really, I guess, changed the way people viewed things like time and space. And one of the results is quite fascinating, really. It's called time dilation. I'm going to show you a remarkable result of just some simple mathematics, simple Pythagoras. It's called time dilation, and we'll see what that is. So first and foremost, let's build a simple clock. So we'll use, let's suppose, 2 mirrors here. We'll build a simple clock, and we'll bounce a pulse of light back and forth between the mirrors. Okay, these two things are mirrors here. And the 2 mirrors are separated by a distance. Let's call it D for distance. So it's sort of like a pendulum, if you wish. A pendulum, think of a pendulum clock. Pendulum swings left and right. And each bounce corresponds to 1 tick of a clock, okay? So it's one second you can think of. And the time between ticks is simply the distance divided by the speed, right? So let's call it capital T for time. It's simply distance divided by speed. Now the speed in this case is the speed of light. C stands for the speed of light. Okay, it's a Latin word which I can't pronounce, but it's just a number. So it's 3 times 10 to the 8 meters per second. In other words, it's 300 million meters, I should say, per second. It's the universal speed limit Einstein showed. Nothing can travel faster than light. And so this relation comes from simply using speed equals distance divided by time. Just rearrange and you get time is equal to distance divided by speed, which is the speed of light. Now let's suppose we put this simple clock on a spaceship, yeah? So here's a spaceship. We'll move this, put this clock system on board. 2 mirrors separated by distance D, and there's a light beam here, let's suppose, traveling between the mirrors. And there's someone just kicking back here on the spaceship. And the spaceship is tagging along at some constant velocity, let's say, V. Call it V, constant speed. Now for an observer on the spaceship, so this guy here kicking back, time ticks away as usual. Okay, so there's no mystery there. And time in this case for the observer, the person on the spaceship, is still given by D over C. Nothing special happening here. But here's an interesting question to ask. What will an observer in another spaceship or someone who's stationary, let's say on a planet, on the surface of a planet, see for this in terms of the clock that's moving past? So for the person on the spaceship, they would see the light beam just going up and down vertically. But what would an observer on the surface of a planet see? Let's take a look. So from everyday intuition, everyday experience, if you even try this on, let's say, a train, if you have, let's say, someone on a train and they've got a ball, like a tennis ball, and they bounce it up and down, the person on the train would just see the ball bouncing up and down as the train's moving. So nothing special is happening there. Before an observer, let's say on a platform, watching the train move, and the person on the train is bouncing the tennis ball up and down, they would see a zigzag sort of motion. And that's relativity. Relativity states that everyone sees things differently. Okay, everyone sees different times and different distances. But the speed of light is constant. The speed of light is a universal speed limit. That's the same for everyone, regardless of how fast you're moving. But time and space, so time and distance, these are relative quantities. They're susceptible to change. And unlike Newton, so Newton believed that there was such thing as absolute space and absolute time. You can think of it as like a master clock in the universe just sitting there in the background. So Newton believed that there was one time for everyone. Similarly for space, everyone measures the same space. But Einstein came along and in his 1905 paper, he proved that wrong. And he said that no, time and distance, time and space are relative and the speed of light is the same. Whereas Newton thought the opposite. So let's redraw this diagram here. Let's have that spaceship again. It's moving at some velocity v. Someone standing on the surface of a planet. Here's the observer on the spaceship, okay, D, and here's the light beam. So D would be measured by the person on the spaceship. However, the person who's on the surface of the planet would see this zigzag motion. It would, in other words, it would take longer for the light pulse to travel between the two mirrors. So as such, that distance we can now call D prime or D dashed, okay? That's the distance that's observed by the person who's stationary, who's not moving on the surface of the planet, okay? So he'd see this zigzag sort of motion, whereas the person, the observer on the spaceship, would just see vertical motion, D. So already we can see there's conflicting views in terms of measuring distances, okay? And this is from everyday tuition. This is obvious if you run an experiment, let's say on a train and a platform, you'd see the same thing. What does this mean mathematically? Well, mathematically, let's draw a right angle triangle. So let's blow up one of these triangles here. Let's take this here and let's blow it up. Okay. Now this is D dashed. Okay, D dashed is here. Right, so just imagine the mirrors, as the spaceship's moving, just imagine the mirrors are here. Okay. That's D dash right there. This is D. Okay, D is that vertical distance, remember, D. And D from here, if you rearrange this using simple algebra, D is just T times C, time times the speed of light. That's equal to CT. And in terms of the velocity of the spaceship, because it's got a velocity, it's moving along to the right here, we can express the velocity, the distance, as just VT dashed. And if you recall from velocity is distance divided by time, all I've done simply is just rearrange this to find an expression for D, which is just this expression here. Okay, and T dashed is the time that's observed by the person, the stationary person on the planet. Okay, so that's a right angle triangle here. And D dash, D prime is the light path. Okay, for the observed by the person on the planet. Okay, that's what they're seeing, D dashed. The person on the spaceship is seeing D. And it's just a matter of using Pythagoras, simple Pythagoras, where this is the hypotenuse here. So D dashed squared is equal to D squared plus V squared T dashed squared. Now we know that D is CT, and we also know that D dashed is CT dashed. Let's plug these in. So we now get C squared T dash squared is equal to C squared T squared plus V squared T dash squared. Now rearranging, cleaning this up a bit, here's what we get. So the C's cancel out, C squareds cancel out. If you rearrange for T dashed, what you get is something amazing. T times the square root of 1 minus V squared over C squared. This here is time dilation. This tells you that moving clocks run slow. T dashed is the time, sorry, I should say, T dashed is the time of the observer on the spaceship. That's their time. Observer on spaceship's time. And T is the observer on the planet. That's their time. V, that's the velocity of the spaceship. And C, that's the speed of light. So let's suppose a spaceship could travel at the speed of light. What would happen? Okay, so the speed of light is 300 million meters per second. Okay, all of that squared, if you divide that by the same number squared, because C is the speed of light, right? These two cancel to give you 1. Sorry, they simplified to give you 1. You get 1 minus 1, which is 0. In other words, T dashed is 0. So relative to someone standing on the planet, the surface of the planet, here, right there, time completely stops. So for someone on the spaceship, they would not experience time at all. Now, in practice, this isn't possible because to travel at the speed of light, you need infinite amounts of energy, which is not possible. The only objects we know of in the universe which can travel at the speed of light, they're photons. And a photon is what light's made of, okay? A particle of light. Photons travel at the speed of light. And amazingly, since the Big Bang, so photons were born just like everything else from the Big Bang about 13.8 billion years ago. Since then, time has not ticked along at all. In other words, photons have never experienced time at all. They're pretty much ageless, amazingly. But that's time dilation right there. Moving clocks run slow. The faster you move, okay, the bigger that V is as it approaches C. T dash gets smaller and smaller, so it approaches zero.